Hello students, welcome to the 42nd lecture of Physical Pharmaceutics 1 BP 302T. I am Dr. Sushma Verma, Associate Professor in the Department of Pharmaceutics, Pharmacy Institute, NIT Greater Noida. Right. In my previous lecture, we just discussed about the Sorensen's pH scale and application of buffers. In our this lecture, we will be discussing the determination of pH. Right. So, how to determine pH? We will be using two methods to determine pH. One is electrometric methods and another one is colorimetric method. Right. In this lecture, we will be discussing electrometric method of determination of pH, and the colorimetric method of determination of pH will be discussed in part 2 of the same lecture. That is, in part 1 we will be discussing electrometric method, and in part 2 of the pH determination method, that is my next lecture, we will be discussing colorimetric method of determination of pH. Right. The pH determination is very important, right, for the maintenance of different dosage form, so that they can be physically, chemically and microbiologically stable to show their pharmacological action, right. And for this determination of pH, I like to have you a brief idea of the electrochemical cell, right, that you must have studied in your +1 +2 classes, right. I just want to have a brief idea of the electrochemical cell. In the electrochemical cell, we have two beakers, right. One, in this we have a solution of ZnSO4 and an electrode of zinc, and this is designated as anode because an oxidation is taking place here, right. And second, we have a beaker containing a solution of copper sulphate, and in this we have a electrode of copper, that is made of copper, and this is termed the cathode because the reduction is taking place here, and both the electrodes are joined to each other by a voltmeter, right. And the cell is completed with the help of a salt bridge, which acts as a bridge between the two beakers, right, and KCl is filled in this tube, that is the salt bridge, and it completes the connection for the whole cell, right. And the cell reaction can be written as Zn solid oblique ZnSO4 aqueous, then copper sulphate aqueous and copper, right. So, how will the reaction take place? Here we have copper sulphate, so and we have zinc and zinc sulphate here. So, what will happen that zinc at this electrode, these electrons at this place electrons will be released by zinc because it is, and the electrons will move through this wire and come through this place to this electrode, and here you will see, you will find 2 Cu plus 2 and they will react with the electrons to make copper ions, right. So, from here we have zinc sulphate, right, it will be dissociated, we have Zn ions plus SO4 minus ions, and these electrons will be taken up by this wire and they will move from this wire to this electrode, and here the electrons will be taken up by copper ions to deposit copper on this electrode, right. So, this is the basics of the electrochemical cell that you have studied, right. The electrometric determination of pH depends on the principle of this electrochemical cell, right. we can use such electrodes for the determination of pH which are altered or whose potential is altered by the hydrogen ion concentration, right. And in this electrochemical cell, one is the indicator electrode and one is the reference electrode, right. So, reference electrode acts at the reference and the indicator electrode will tell you the reading of the test solution, right. So, the electrometric determination of pH, the principle lies here is that the indicator electrode whose potential changes with the concentration of hydrogen ion activity, right. So, if there is a change in the hydrogen ion concentration, so the potential of the electrode will automatically change. If we have such type of an electrode with us, so it is suitable for the determination of pH of the solution, right. And for that it is known as the indicator electrode, because it will be indicating the pH of the solution, right. And for that we have two examples, one is the hydrogen electrode and another one is the glass electrode, right. These two indicator electrodes can be used for the determination of the pH, right, because hydrogen electrode in that case also it depends on the hydrogen ion activity and the glass electrode also depends on the activity of hydrogen ion, right. So, these two indicator electrodes are used for the determination of pH, and second we require is the reference electrode, that is the standard electrode, right. And for that we have calomel electrode, it can be used as reference electrode, and we have silver chloride electrode, right. These two are the reference electrodes that can be used, and indicator electrodes which can be used for the determination of pH are hydrogen electrode and glass electrode, because their potential depends on the hydrogen ion concentration, right. And the National Bureau of Standards determines the pH of its standard buffers, right. The National Bureau of Standards recommends a hydrogen indicating electrode and a silver chloride reference electrode, right. It recommends hydrogen indicating electrode, it can be any one out of the two, but generally this glass electrode is used, right. This glass electrode is generally used for the determination of pH, because it is quite sensitive as compared to the hydrogen electrode, right. So, the National Bureau of Standards recommends the determination of its pH of its standard buffers in a cell composed of a hydrogen indicating electrode and a silver chloride reference electrode, right. So, silver chloride acts as the reference electrode as recommended by the National Bureau of Standards, and you can use either of the two electrodes as the hydrogen indicating electrodes, right. So, next is the hydrogen electrode, right. So, this is the diagram showing the standard hydrogen electrode. In this we have here a platinized platinum electrode, right. We have a platinized platinum electrode here, right. We have a piece of metal that is being platinized, right, and it is attached to a platinum wire which is further joined, right. So, we have a platinized platinum wire, right, and that is housed in a chamber, right, which is like a rectangular shaped below, and it is like a test tube above, and there is a opening, and from this we can add hydrogen at 1 atmospheric pressure, right. From this opening hydrogen gas can be added into the housing, right, at 1 atmospheric pressure, right. So, this is the hydrogen electrode, and here we have 1 molar solution that can give hydrogen ions, right. So, the potential of hydrogen electrode depends on the hydrogen ion concentration. So, it is suitable for the determination of pH, right. And so, how does the reaction takes place at the hydrogen electrode? At left, oxidation takes place and H2 plus 2 H2O will give 2 H3O plus. This is the activity of hydrogen ion plus 2 electrons, right. So, this is the activity of hydronium ion. So, this will be giving you the pH, this will be giving you the pH, and at right reduction will take place, right. That will be of the right, we here we take it as the reference electrode. By right here I mean that we are taking a reference electrode, by left we are taking the indicator electrode, right. So, the indicator electrode here is the hydrogen electrode, right. So, hydrogen gas is aired into the housing and it will act with hydrogen, two molecules of water to give 2 hydronium ions, right, and plus 2 electrons. So, these hydronium ions will be contributing towards the determination of pH, and at the reference electrode which we have taken up as the mercury chloride, right. So, this at this the reaction take place like this, Hg2Cl2 plus, this will take 2 electrons that were being given by this electrode and it will make 2 Cl minus plus 2 Hg, right. The overall reaction, the overall cell reaction of the comprising of the 2 electrodes, one is the indicator electrode, that is the hydrogen electrode in this case, and another one is the reference electrode, that is the mercury chloride electrode, right. So, the overall reaction can be written as H2 plus Hg2Cl2 plus 2 H2O will give 2 hydronium ion plus 2 Hg plus 2 Cl minus, right. So, this cell is represented as, this was the cell reaction and this is the representation of the cell, right. So, it is platinum H2 1 atmosphere, right. So, the platinum the piece of platinized metal, right. Here H2 gas is pumped at what atmospheric pressure, and here we have what we got, the hydronium ion, which will be the our determination of the pH. From here the determination, this is the x which we want to calculate actually, right, and this is the KCl, this is the salt bridge, gives Hg2Cl2 Hg, right. So, these are the reaction that takes place at the hydrogen electrode, right. The EMF of the cell is, right, the EMF of the whole cell is given by E cell is equal to EH2 gives 2 H3O plus plus EHG2Cl2 gives 2 Hg, right. The EMF of the cell can be given by this equation. The potential of the hydrogen electrode at 25 degree centigrade and a partial pressure of the hydrogen gas of 1 atmosphere is written as EH2 is equal to E naught H2 gives H3O plus minus 0.0592 log, this is the concentration of hydronium ion upon 1 atmosphere. Under these conditions E naught is 0, right. So, the total cell equation, the EMF of the cell was given by this equation, and the potential of the hydrogen electrode at 25 degree centigrade is given by this equation, right. And under these condition at 25 degree centigrade, the E naught is 0 and the equation reduces to EH2 plus minus 0.0592 log activity of hydronium ion. So, this is what we are interested in. So, these are basically the cell equations that are derived from the Nernst equations that you must have studied in your previous classes. So, I am not taking up them in detail, I have just taken them briefly here after describing the electrochemical cell. So, these are the equations that are taken up when the indicator electrode is the hydrogen electrode, right. These are the cell, and so this is the hydrogen ion activity, and since pH is equal to minus log of hydrogen ion concentration, right. So, we are taking up dilute solution. So, this is pH is equal to minus log of hydrogen ion concentration. So, here EH2 is equal to minus 0.0592 pH. So, the potential of the saturated KCl calomel electrode in the reduction reaction is this one, right. So, we know the potential of the reference electrode, right. So, it is given to be 0.242 volts at 25 degrees centigrade, right. So, we have got the potential of the reference electrode, hence we can put this value E cell is equal to 0.0592 pH plus 0.242, right. So, and the pH of the solution that is to be determined can be given by E cell minus 0.242 divided by 0.0592, right. So, in this way we can get the pH of the test solution, right. What we can do is we can put the test solution and get the potential from the indicator electrode, because we are knowing the potential of the reference electrode, we can put the value, and from there we can calculate the value of the indicator electrode, which will be indicating the pH of the test solution, right. Next electrode which can be used as indicator electrode is the glass electrode, right. So, the glass electrode consists of a glass membrane, right. It is a pH sensitive membrane, right. It is a glass bulb, right, that is composed of silica and which is incorporated with lithium ions, right. And this glass tube is blown up in the shape of a bulb at the terminal, right. And this is a AgCl electrode here, and these are two, one is this and second one is this, and this is a liquid junction which makes a, you can say a contact between the two solutions, and we have a thermocouple, we have outer solution and inner solution, and it is temperature regulated, right. So, temperature regulation is there for pH determination, because we have earlier discussed in our previous lecture that the temperature affects the pH of a particular solution. So, temperature maintenance is must. So, so in this glass electrode, this can be a single electrode itself which has a glass membrane that is pH sensitive, and it has also get a reference electrode in it, that is silver chloride electrode, right. So, we have a combination of two here, one is the indicator electrode glass electrode and second was is the reference electrode that can be silver chloride in this case, right. Next we will see how the EMF of this total cell can be calculated. The typical of the membrane type electrode, which is the most widely used pH indicating electrode, is the glass electrode. This is highly sensitive one. So, it is frequently used. Hydrogen electrode can also be used as the indicating electrode, but generally in trend it is a trend that glass electrode is mostly used. So, it is a conventional electrode which includes an acidic electrolyte solution of 0.1 normal HCl. So, this 0.1 normal HCl, which is a part of this acidic electrolyte, will form the source for the hydrogen ions, right. The complete cell using a saturated calomel reference electrode cell can be represented as. So, this is the equation for the complete cell, right. In this one we have the source of hydrogen ions, this is 0.1 normal HCl solution which is present in the glass electrode. This is the source of hydrogen ion. So, if this concentration changes or how this concentration modulates will determine the pH of the test solution. Right. So, the solution of the equation for the cell is silver chloride 0. normal HCl, that is present in the glass electrode, glass membrane, and unknown solution, and KCl salt, this is the salt bridge, KCl saturated, and Hg2Cl2 Hg, and this is the hydronium ion concentration. Right. So, this is the total cell equation which can be written by taking glass electrode as the indicator electrode and another one the reference electrode. Right. The total cell potential in this case can be calculated by this equation, and it can be written as E cell is equal to ESC plus EASYM minus EAGCl Ag plus 0.059 pH of unknown minus pH of hydrochloric solution, right, where ESC arises at the boundary of Hg2Cl2 Hg, right. So, ESC, this is the standard calomel electrode, right. So, this potential is due to the reference electrode, right. So, this is this saturated calomel electrode, this is the standard electrode or the reference electrode, and this potential ESC is due to the potential of this reference electrode. Next we come up to this ASYM, right. This comes from the two boundaries of the glass membrane and is equivalent to differences in resistance that arises owing to variations in manufacturing, right. And this we have two glass membranes in the glass electrode, and due to the two boundaries of the glass membrane there is some resistance, and due to that resistance which are due to the manufacturing variations, this term is generated which is known as EASYM, right. Next we have the potential as EAGCl Ag, this arrived at the boundary of silver chloride electrode, right. Though the pH of HCl solution term comes from the 0.1 normal HCl solution, while the pH unknown is the pH of the solution being determined, right. So, this 0.1 normal HCl solution, this terms comes from the 0.1 normal HCl that is present in the glass electrode, right. So, it is the source of the hydrogen ion concentration which makes it a indicator electrode, and the pH is the unknown, is the pH of the test solution which you want to determine, right. So, the pH is obtained from the cell EM if the pH of the internal solution 0.1 normal is constant, right. So, these manufacturing variations we can just omit, because these are due to the variations of the different manufacturers which are manufacturing the glass electrodes. If we keep a single glass electrode, so for that particular glass electrode the variations of the cell that are due to manufacturing can be minimized, right, that can be put to constant. So, this error can be eliminated, right. So, if we remove those variations, right, of the manufacturing, and if we keep a single glass electrode, so the variations are kept constant. So, the cell equation reduces to E cell is equal to E constant plus 0.0592 pH, that is of the unknown solution, or pH is equal to E cell minus E constant upon 0.0592, where E constant is sum of all the boundary potential arises from the 0.1 normal HCl solution, right. So, E constant इस टर्म में हमने जितनी भी वेरिएशंस थी उनको इनकॉर्पोरेट कर दिया, राइट. सो दिस elaborated equation can be minimized to this equation by putting all the variation in this E constant, right. So, this E constant is the sum of all the boundary potential arising from the 0.1 normal HCl solution, right. So, we have put all these terms in this constant and the equation is reduced, right. So, next we have the equation as pHs is equal to Es minus E constant divided by 0.0592, in which pHs is the pH and Es is the EMF, right. So, pHs is the pH and Es is the EMF of the NBS reference buffer solution. Subtracting this equation from the previous one in order to determine the undetermined E constant, right. We want to determine this E constant, we want to get its value. So, we have this expression as pH minus pHs is equal to E cell minus Es divided by 0.0592, or pH is equal to pHs plus E cell minus Es divided by 0.592 operational or practical definition of pH. So, this is the operational or practical definition of pH that you can use to calculate the pH using a glass electrode as the indicator electrode, right. So, what we can do is to determine the pH of the solution, what we can do is we can have a pH meter here, right. So, it has got all its aperture, right. There is a knob here, there is a temperature setting here, right. This is a knob, that is asymmetrical potential, potential adjusting knob. Here we have stand bias and there is an on and off switch here, right. So, this is a pH meter, right. You must have seen in your laboratories. So, this pH meter can be attached to a glass electrode. It can be attached to a glass electrode or an indicator electrode, and the total cell is completed, right. So, if you want to determine the temperature of a particular solution, what you can do, right. You can immerse this glass electrode in that particular solution. So, we take a test solution, right. This is a beaker and we take a test solution in it, right. This is a beaker and we take a test solution in it and we put the glass electrode here and it is attached to the pH meter. If this glass electrode is attached to the pH meter, then the circuit is complete and the pH of the particular solution can be determined. So, how it has to be determined? So, first of all there are some standard buffers, right. So, of different pH are there. So, it can be of 4.9, 9 and 6.5. So, different range of pH buffer solutions are available to us. So, what we will do, first of all we will put the buffer solution, right. We will what we will do, we will take the pH of the standard buffer solutions, right. So, we will first take a buffer of pH 4.9 and first what will we do? We will adjust this knob for temperature compensation, right. So, temperature is one of the important factor that is affecting the pH of the solution. So, temperature knob is regulated, then the pH of this buffer, this asymmetrical potential error is given a 0 error, right. So, this error is minimized, this is knob is set and the pH of the buffer solution is determined, right. It is done 3 times and we have to determine the buffer pH of different standard buffers. 3 buffers are to be determined and then the pH of the test solution can be determined, right. You can put the solution here. So, it will change the hydrogen ion concentration of the glass electrode, right, and if this concentration is changes, this will be detected in the pH of the cell. With this can be calculated using the equations that we have discussed previously, right, and the reference remains the same, the Physical Pharmacy by Alfred Martin, and this was all about the conductometric determination of pH.